the invitation and for organizing this session in the circumstances. I'm sure like there's been lots of difficulties, so thank you very much for all this work and for having me here. Today I'm going to talk about this work that is a joint work with George Lira, Red Maceo, and Alessandra Bruda, and I'm also going to try to avoid the technicalities. At the end, I'm going to just say a few things about the technicalities, but I want to pose the problem and try to be clear why we're studying what we're studying and how we address the problem. So I'm going to start by talking about the mean curvature flow, which is the gradient flow associated to the area functional. I'm going to motivate the study of this. Actually, the beginnings of this equation come from material science, where they were trying to study energies that were, I mean, they were thinking about a material in two phases, actually, usually, I don't know, called phase 1 and phase 2. And they had an interface that was evolving and trying to minimize energy, and that energy was proportional to the area of that surface, the surface area that divided these two phases. So it was a natural problem to minimize area. And if you want to study a static problem, you're studying critical points of the energy functional that is associating energy with some boundary condition. Usually Neumann boundary condition would be the natural thing here. And yeah, and then what you get is the study of minimal surfaces, but there's also interest in seeing how the interface evolves and gets to that minimal state, basically. And that's what's the mean curvature flow. And that was the work that was developed 50s or 60s in material science, but in math, in mathematics, much of the work has been done later, like in the 80s, late 70s, 80s, until now. So I'm going to talk about the geometric problem a little bit, what is known, that is not exactly the application that I was mentioning here, but I'm going to go back to that. And what you see when you look at the Euler-Lagrange equation of this functional here is an equation that is time dependent because you're evolving in time to minimize. And the best way to do that is something that is proportional to the mean curvature. In very few minutes, I'm going to be talking about one-dimensional problems. So this mean curvature is just going to be the regular curvature of the curve. But this is sort of the more general setting that you can see here. And when n is equal to 1 in the curve case, that is the curve case that I'll be talking about. This is called the curve shortening flow. So I'll be mixing up the words because for me, everything mostly is curve shortening flow, but the general term is usually mean curvature flow. And the study of these, as I said, in mathematics, a lot of it was done in the 80s. And the simplest case for many reasons is to study closed curves. That's the simplest thing that you can do, embedded, no intersections. I'm going to say a word why this is the simplest case. But in particular, because if you want to compute some examples, the simpler example that you can try to compute is the evolution of a circle. And this you can compute very explicitly what happens, actually. You can see that if you want to find a solution of this, if you take something that is a circle for every time with radius, here I'm going to make a mistake for sure, 2 minus t, I think. I might be missing a constant here. This is going to be a circle evolving by mean curvature flow that is going to become a point in a finite time, 2 in this choice of parameters. There's some choice here because, I mean, you have, of course, an initial radius that I'm sort of ignoring here. In this case, it's square root of 2. But I mean, you can, of course, do it for other radiuses. And the feature that I want to highlight in this example is that this becomes singular in finite time. So it's very important to understand how the singularities develop in general, because even in the simpler examples that you can compute explicitly, you see that you have singularity. So the question is this all that can happen? Can you have a different type of singularities? In the problem that I was talking about at the beginning, in the motivation, in the material science problem, if you have a boundary condition, is that better or worse? Do you have less or more singularities? Are they the same, etc.? I mean, this is the kind of question that you want to understand usually when you study this. So, well, then you go from curves to higher dimensional things. And the first thing that people did was try to look at examples, and they observed that In fact, you can have other types of singularities. It can be more complex. And a classical example here is that if you have a dumbbell type of surface like this one, depending on the ratio between the size of these balls and this neck, you may have singularities or not, actually. And the singularities can be point singularities, like a neck pinch like this one here, or you can have singularities like the other one. If the neck is very thick, you can see also singularities of the other type. I mean, you could also be becoming more like a sphere here and then going to a point. So even the type of singularities that develop are kind of fine. It depends on adjusting some parameters. So it's not easy to understand in general what the singularities are for these kind of flows. Okay, so as I said, the case of curves is a simpler one, and in fact that one is better understood in the case of embedded curves. So if you have something that is embedded and convex, it is known that the singularity that I showed you at the beginning for the unit circle is the model singularity. So every singularity that happens in that case is actually something that is becoming convex in finite time, and then when it becomes convex, then it converges to a point approaching a unit circle when you rescale. So you see something that is more and more similar to a unit circle. So the example that I just showed before of the dumbbell is something that can only occur in dimensions that are bigger than one, but you don't expect to have that kind of behavior when you're talking about curves. So somehow the case of curves is a nicer case, and that's why soon I will be restricting to that case, but in a slightly different setting. With the talk of, with the topic of singularities, of course, from the PDE point of view, and something that I haven't mentioned is what do I mean by a solution of the flow. Up to here, everything that I've been talking about is classical solutions. I'm thinking about solutions that have two derivatives, and then I can define what the curvature is, etc., etc. So I mean, it's something that is very geometric, but from the PDE point of view, one might think that you can talk about other types of solutions, and that actually was work in the 90s about trying to define a family of what weak solutions may be and what kind of objects and singularities I allow by giving different notions of weak solutions. I'm not going to talk about this, but there's more than one notion, and if anyone is interested to know more about this, the notion that is going to be important here is the brachyflow notion. That is these are solutions that are in the geometric measure theory sense that allow for things that are not surfaces, but you can define what the curvature is. So this is the idea. And then because I'm defining a wider class of objects, I can think about things that are not manifold. In particular, the example that is going to be important here is this one here. I also drew a different kind of thing that is almost a surface. It's just not regular, almost a curve actually, but has one singular point. And for all these things, this is going to be a well-posed problem. The second example that I didn't put a domain there, but I could have like enclose this into a domain omega, was actually one of the original problems that Mullin studied in the 50s and 60s, where he was thinking about a material that actually have three different phases, so phase 1, 2, and 3, and you had transitions in all these layers. So all these curves are trying to minimize energy by minimizing the length. I'm thinking about something that is symmetric, so I'm just thinking about curves in this case. But you have always a triple point here. That is what soon I'm going to call a node. And that sort of poses analytic problems when you try to think about this motion here, because basically you are going to have a system of equations of three curves that each of them is going to evolve by curve shortening flow, but also they will have to meet here. And to pose that as a problem, you have to think what is the correct condition that you have here. And on top of that, just like from the point of view of how these things have been studied before, where we were thinking about classical solutions, one of the main tools that you use or that people use is maximum principle. And when you have the system here and the sort of singular point in the middle, you will be losing all possibility of using, maybe not all, but many of the possibilities of using maximum principle to study the evolution. So you need to develop sort of new techniques to understand this problem that was one of the first problems in the area, actually. So this is the thing that I want to talk about today, actually. Okay, so I'm gonna be explaining the title now of my talk, that I'm talking about networks in general. So I can have more than 3 curves. I can have families of curves. Each of these is gonna be evolving by curve shortening flow. As I said before, to have this well posed as a PDE problem, you need some condition, well, at the boundaries, at the outer boundaries, of course, but this is, as I said before, like a more standard choice that could be Dirichlet or Neumann or something, you know, like one of the standard choices. But we also need to pose conditions at the nodes. And I want to explain the choice of condition that we need to have this as a well-posed problem. Okay, so let me just skip this. And as I said, this is exactly what I said. So each curve is going to satisfy the curve shortening flow equation. And the question here that you should ask yourself, and if we had a bit more time, maybe I would ask you, or if we were in person, is if you have like a simpler question, if you have 3 points and you want to find a minimizing connection between these 3 points, so you want to find some sort of network that connects the 3 points and has minimal length, what would that be? So that would be sort of the first question that you want to ask here before trying to decide what is the correct condition of these triple points. And then after that, you could ask the same question, putting more points on the circle. I did 3 and 4 here. And actually, this kind of question is something that is in some sense an elementary geometry question, something that you can do without many tools. And the answer, maybe some of you know, maybe many of you know, but for me it was surprising the first time I saw it, is things that have this shape, that look like this, and all the angles here are equal and are 120 degrees, so 2 pi over 3. And this is kind of optimal. I mean, this is optimal, but it cannot be found always. Of course, I mean, I drew a circle here, everything is sort of very well distributed, but you can sort of imagine that if you draw the points closer together, for instance, you may have collapsing of some of the curves, or if the domain is not a circle, but something that is non-convex, then the lines could be coming out of the domain. So this is a very particular thing. It's something that locally makes sense, but you have to be a bit careful with the condition. And then if you want to look at the problem with more nodes, this is globally true. I mean, always if you have a minimizer that you don't always have, as I just said, this is going to be something that the curves meet in 3 and they have 120 degrees among them. So this is the condition that I'm going to pose. And the reason is that because this is a length minimizing condition. And this is called the Herring condition, actually. This was proposed in the context of material science, actually. So, of course, I'm going to ask for this not to separate as well, because then it would stop being a network and it would stop making sense in terms of the problem that I was trying to address to start with. Okay, and then when you're looking at evolution of networks now, you may ask the same questions that you asked for the regular case. That is, what kind of singular behavior do I see? What do I have to worry about? Do I always have an evolution, etc., etc.? Is this evolution unique? All this kind of thing. So here I wrote the equations, but I'm just gonna skip this for now. If someone's interested in seeing them, I can come back to it. This is the evolution equation that you arrive to. This is the condition that the curves meet. And this condition here is the Herring condition that the angles are all 120 degrees. You can summarize this into these 3 equations. Okay, so as I said, I want to understand all the basic questions. First, existence and uniqueness, and then what kind of singular behavior we can see for that. even the existence problem is not trivial. I mean, there have been many people that have worked on this. One of the issues with this is usually to solve this system, you need these conditions, but also at the meeting point, you usually need higher compatibility conditions. I mean, you want the conditions to be satisfied to a higher order. I mean, if you take derivatives of the condition, you want the condition also to be satisfied to apply standard methods to solve the equation. So there's I'm going to show you a long list of people that has worked on the existence of this problem and trying to relax all these higher order conditions if you want to find a solution. So all these people here, Kinderlehrer, Liu Bronzer and Reitich, and I'm missing a comma there, Mantegas, Nova, and Tortorelli, all of them worked in this problem. And the last two papers, what basically they tried to do was to relax these higher order compatibility conditions. But you still needed to have the compatibility condition to some extent to be able to show existence to the problem. And uniqueness is actually a more tricky question, as I'm gonna mention in a few minutes. So I'm gonna skip the discussion of uniqueness for 5 more minutes and tell you that, I mean, that in fact, this is something that one needs to think about more carefully. So let me go first to the singular behavior, and then I'm gonna go back to the uniqueness soon. Okay, so here I'm trying to depict pieces of networks just to tell you what happens with the singularities. And I want to go back to my example of the circle several slides ago, where we can compute, in that case, an explicit solution, an explicit evolution of the area that is enclosed. This is a computation that on the plane you can always do because you have the Gauss-Bonnet formula. So you can, it's not hard to see that if you have an evolution, how would the area that is enclosed evolve? So the first thing that one would think, okay, if I have any loop, this should contract to a point, and then, well, what does it happen then? And the computation tells us actually a bit more surprising. That is, if you have less than 6 sites, the evolutions that the singularities that you develop are actually like this. So the curve stops being regular because it's not meeting in 3s clearly anymore. But if you have 6 sites, actually the area is preserved. So if there are singularities, it's not because of the collapsing. I'm gonna show you what can happen in a minute. And if n is bigger than 6, the area grow actually. And if you are in a domain as before, clearly you cannot grow forever. I mean, something else has to happen. I mean, at some point you will be hitting the boundary and you will have other types of singularities. So let me tell you what is the 4th type of singularity that you can, or behavior that you can have here. That is, in fact, even if you have something that has no loops, you may have collapsing. You may have that some curves are disappearing. You may have things like that. And then again, here, this is not anymore regular. The curves are not meeting in 3 and certainly not in 120 degrees, all of them. So as I said before, even to show, I mean, existence of something of this sort is not direct, and it cannot be done by the methods that existence was proved in the previous cases. So this is the problem that we're interested in, actually, to show existence when you are starting from something that is non-regular. So meaning that we have a family of curves that meet in one node. Of course, you could have something bigger, but and the method actually works. But I mean, I'm just going to concentrate in the simpler case that is one node and many curves coming out of that node. You will see in a few minutes that the discussion can be extended actually to more complicated networks. So our main theorem is basically existence for this type of networks. I'll show you here the theorem itself. Maybe it's a bit long, but this is all that is saying really, that if you start with something that each of the curves is regular, but they do not satisfy the Heron condition, so they all meet at one node, then you will have a solution that is regular for positive times, at least for some short time. It could be that after some time, other singularities are developing. And in fact, these solutions in general are not unique. You can we can, I won't say we can classify, but we can describe what would be the problem. I mean, where is the non-uniqueness coming from? So actually uniqueness is not expected for these flows, and this was known before because you can compute very explicit examples, or you can see very explicit examples where you have non-uniqueness. This is a similar, this result, there was a similar one before, not many years ago, by Tom Illman and Andre Neves and Felix Schulze, but their methods are different, and their method has advantages in certain situations. They can prove uniqueness in certain situations, but our methods apply for a more general class of networks. So I just wanted to mention that. And in our case, what we're using is micro-local analysis techniques to try to give a more accurate description actually at the node, and to understand exactly what I was saying before, for instance. I mean, why you may not have seen uniqueness for the evolution, and what kind of thing can you see in this non-unique part. And I see that I have only 8 minutes. So let me try to briefly describe how the proof goes and what are the methods that we're using. Okay, so the basic idea of micro-local analysis is to introduce coordinates that allow you to understand the singularity better. If you're not familiar with these ideas, you can think about polar coordinates, which everyone knows. And in polar coordinates, when you're away from the origin, the description in polar coordinates or Cartesian coordinates is exactly the same. But as r approaches to 0, you may see in principle different behaviors for different angles. And basically, if you have a singularity at the origin that can be captured by these different angles, then you'll have a better understanding of the singular behavior. So one can understand this as blowing up the origin and adding an extra boundary here that should sort of contain the information about the singular point. However, if you're adding a boundary, somehow in terms of the PDE problem, you're adding one boundary and you need one more boundary condition. So the question is, what kind of boundary condition should you impose here? Sorry, because of the time, I just skip this, but I should say a word about this. I'll go back before going back to that discussion. That is what I care about. But when we are in the case of a parabolic problem, somehow it's not anymore R2. I mean, the time variable and the space variable have different homogeneities. So you don't use exactly polar coordinates, you use coordinates that sort of respect the difference. And this would be the natural set of coordinates. I mean, basically, the homogeneity of these two are satisfy the same relation that they have in the heat equation. So when I'm talking about R in the coming slides, I will be thinking about something of this form. But let me go back to the discussion of the boundary condition that you impose here. So let me see, I have 5 minutes. So one important thing to understand the singular behavior is to understand what kind of boundary condition should one impose in this kind of thing. In the case of curves, actually, it's not one boundary condition, but it's one additional boundary condition for each of the curves. And here I'm drawing a picture that I even have some additional curves, and I will say that in general you may have additional curves. And the question is, what is the thing that I'm adding here to be able to study the problem in a way that is better somehow than what we had before? And the answer to that comes from what happens in the case that I drew at the beginning. That is something that, like, just two straight lines that meet at a point. In this case, one can find not explicit, but almost explicit solutions. So these are self-similar solutions, so are solutions that have the same shape at every time, and that you can parameterize in this way. So when t goes to 0, what you observe is that you see just the behavior of gamma 0 at plus infinity and minus infinity. And in general, if you have a singularity in curve shortening flow of this type, or like an initial condition of this type, or something that has a corner, when you do the blow up here, when you try to blow up this point, you should see a solution of this type. So the question, the natural question, of course, is going back to my network problem. What is the equivalent thing for networks? And well, the equivalent thing for networks is exactly the same thing. So you, instead of 2 lines, you will have n lines. And in this case, well, you want to prove existence of this. And this is a theorem that Red Maceo and myself we proved several years ago, that if you have n curves for any n bigger than 2, then you always have a solution, but that solution is not unique. That solution in general is not unique, and they're not classified. We don't know how many of them we have. So here I attempted to draw a solution for my previous one. Not very good. This is a connected solution, but yeah, I mean, this is in general not unique. And let me give you an example why this is not unique. Okay, so if you take this, you recall what I just said about the case of 2 curves, that we know that we have self-similar solutions in that context. There's one very simple self-similar solution that is just taking these 2 curves. So this red curve is coming out of these 2, and this one is coming out of these 2. But then even from there, very naturally, I mean, this is somehow I made a choice there that could have been different. I mean, I could have made this choice. So here you already have 2 solutions, 2 different solutions, and none of these are networks, right? But our theorem, the one that I just mentioned, says that you also have a connected solution. So you have these 2 solutions, and then you also have a solution that is a network, that it is something that looks like this, that is self-similar, has the same shape for every time. And in fact, you can show that this red line that I drew here, I mean, these 2 red lines that I drew here, this is not what I want to do, this red line and this red line, are inside the green arc that I had. So this is sort of a maximal solution, and this other solution is something that is inside. Even more, I mean, because of the symmetry of the problem, you can imagine that I can even, for this problem, have a fourth solution. The fourth solution would be just a rotation of this, because the problem is symmetric, so this is also a solution. So in this case, you have solutions that are connected, solutions that are disconnected, and you have several. So somehow, even in the simpler case, you have many solutions. And of course, then for the general case, you expect to have at least as many solutions as you have for this simpler case, especially if this is smaller than somehow the singularity. So now, in the last minute, let me just say one word. How do we proceed now? So the main idea now is that basically in the new coordinates, the boundary condition that I need to add is exactly one of these self-similar solutions. I can choose any of the self-similar solutions, and this is going to give me a new boundary condition, and we will be able to solve with that. The idea for solving is kind of a more standard idea. We use a fixed point method, so we construct an approximate solution using the self-similar solution that we had. Basically, we write this as a power series. Each of these is going to satisfy an ODE that we cannot explicitly solve, but we can show that it has a solution. Let me show you what the first one is. The first one is this one. And the first one is exactly the solution of the self-similar one. So this is exactly the solution that, I mean, the equation that self-similar solutions satisfy. So this is a choice that we have to make, is a boundary condition that we have to give. We choose one of these self-similar solutions, and then all the other 8 AJs are going to satisfy recursive equations that depend on the previous one. So basically, when I choose a self-similar solution, then I can construct a full approximation, and then we're going to linearize around our approximator and show estimates for that linearized operator, and show that then you can, by a fixed point method, you can find an actual real solution for that. I'm not gonna go into details. I wanted to show you a little bit of the estimates, but I see that I'm already 1 minute over time, and I don't want to take more time. So I think I'm gonna stop here. Thank you very much for your attention.
Thank you very much, Mariel. So again, because of time constraint, we are going to skip the questions. I hope that by tomorrow the chat will be enabled so that people can ask questions individually.